Okay. Thanks for the first introduction. Actually, it's my best time during my PhD study. Thanks for everyone come to my PhD defense. Today I will give a topic. My PhD topic is towards plausible collaborative machine learning, privacy, efficiency, and fairness. Here is the outline, and I will first give an introduction about what my work and motivation stuff, and also I will introduce three of my works. One is differentially private ADM-based distributed machine learning, and then I will introduce differentially private and communication efficient decentralized gradient descent, and my third work is related to differentially private and fair machine learning, and finally I will introduce a future work and a conclusion. So, machine learning technique was proposed in 1956. However, this technique was not well recognized until the early first century. When he first proposed the idea of artificial intelligence, which is amazing at that time, and was people was very interested for a while on this like a brand new concept, right? However, due to the hardware limitations and complexity, the real world problem, this idea was unrealistic. So in 1960 to 1980s, Edward developed an expert system, which is giving the reimburse to artificial intelligence. However, the hardware data collection was still not reaching the needs of machine learning algorithm. So the result was not ideal enough to be applied to real applications. Fortunately, in the early 21st century, the development of hardware multi-core CPU and GPU and grows rapidly, and billions of data also generated by phones and IoT devices. So they push the machine learning and deep learning into the front of stage. So one question is here is like, what does the big data come from? Like we can think of an example like an IoT example, Internet of Things. Like the data come from like maybe smart cities, smart homes, smart wearable devices, and the data is sent through billions of sensors. And we can think of the healthcare data through the patient records, medical images, and also like some data from the web content like search engine, data center. And we have a lot of data from financial services like banks and insurance companies. So as we all know that making model bigger and feeding them into feeding them more data, and we can achieve better performance in terms of learning, right? So the case is if the data may have different owners and localities. So directly sharing the sensitive data may incur the serious privacy leakage, and which is also forbidden by regulations, for example, HIPAA and GDPR. And so the distributed machine learning becomes a promising solution to conduct tasks over distributed data. The distributed machine learning has numerous applications. For example, autonomous driving. If you consider a car or every car as a machine and devices, then we can collaboratively train a model to learn the probability of a traffic jam several miles away, or like the traffic jam, the potential traffic jam I'm going to have in 1 hour or 2 hours or something. Another example is here is Google Gboard input prediction. So everybody uses smartphones. When you want to input something, actually the machine or the machine model can predict or can guess based on the different scenarios and what you input at the beginning. So the Google performed the distributed machine learning over the people's smartphones and then return the newest model back. So you can use that to better predict what you want to input. And also there are some other examples. For example, like speech recognition and face recognition. Next, I will introduce like because we know the machine learning can memorize the training data. So many works show that attacker can infer sensitive information of the private trained data from the shared model or the gradients, such as the machine model inversion attack and the membership inference attack. So here is example for model inversion attack. So suppose this is a figure recognition model, and there is in the cloud, this model is trained by a lot of faces, and the attacker can only has a person's name and whose image this one is used to train the model, and in the train phase, right? So the attacker can produce a approximate image of this person by attack the download the model parameters, either black box or white box. And the second kind of attack is called membership inference attack. In the membership inference attack, the attacker tries to identify whether a specific data sample is a member or not, or like this sample was used in the training data or not. So the technique they use to launch membership inference attack is based on this one. Here, this is a probability distribution. For example, we have a black box or white box model, and we have a lot of data samples. For example, this model is trying to identify the cars tab, the car tab for SUV and sport or something. And we import this one, import this figure into the model, and we got the possible prediction distribution, right? We can see the SUV is here, so the model can predict this is a SUV. This picture, this car type is a SUV. So since the difference between the output distribution, regardless of the input, some like input from train data, input not from train data, the output distribution is different. So the attacker tries to recognize this difference through a binary classification. For example, binary classification, so it can predict whether the data is from train data or not. So to deal, as I mentioned at the beginning, like there are a lot of privacy concerns, like a model inversion and membership inference attack. To deal with such privacy leakage, there are two ways. One is to put a cryptographic method on top of it, such as secure multi-party computation. However, like this method introduces large computational overheads, especially in large scale of deep learning. So moreover, it cannot provide the protection of the final model. That means like the final model can still suffers from what I said, the inference attacks. And the other method is to add noise into the critical part of the whole training process, like SGD or objective to provide differential privacy. So, which can not only provide the privacy for the intermediate model update, but also for the final model. However, this method suffers from accuracy loss, performance loss due to the noise injection. So our first goal is try to design some techniques based on differential privacy for distributed learning, while keeping the model utility or covariance. So because of the size of a learning model increases, and this is number of parameters, and this is ImageNet top 1 accuracy, and increases, which is currently trained in large scale distributed learning. The model exchange among the agents become a significantly communication bottleneck. So our second goal is try to develop a distributed optimization method while keeping the communication efficiency and power protection. Moreover, like one intuitive fact of machine learning is that the machine learning models are not neutral. What that means? That means like some applications are biased to certain work groups. For example, for facial recognition here, used in the real world in the San Francisco. San Francisco people voted against the use of facial recognition system because they are proven to errors when used on people with dark skin or women. So another example is in job application. So in 2014, a team of software engineers was build a program to review the resumes. Unfortunately, in the next year, they realized that the system was discriminating against women and for technical roles. So the recruiters did not use the software to evaluate the candidates because these discrimination and fairness issues. So our second goal is try to design machine learning algorithms with fairness and differential privacy guarantees. So this is the overview of my PhD work. To deal with the challenges of privacy and model utility, we propose a differentially private ADMM-based distributed machine learning. To deal with the privacy concern and communication overhead and the system efficiency, we propose a differentially private and communication efficient decentralized gradient descent. And to deal with the challenges of privacy concern and fairness issues, we propose some algorithm related to differentially private and fair machine learning. I will first introduce my first work, differentially private and AEM-based distributed machine learning. In this work, we are going to focus on this problem. So here, like we consider a connection network of A and A agents. Each agent have is a local private data set, D1, D2, Di, and the objective is to jointly train a classifier over the union of local data, which can be formulated as an empirical risk minimization problem, ERM problem. You can see this problem. It includes the number of agents and the local data Di, and L is the loss function, and R theta is the regularization term to prevent overfitting. So commonly, there are two ways, two different types of approaches to solve this problem in a distributed way. The one is an alternating direction method of multipliers, ADM based. The other one is a stochastic gradient based. So our first work is based on ADM based. So in order to solve the above EM problem in a decentralized manner, we first to formulate the EM problem in this formulation by introduce a local variable and the auxiliary variable theta I rho ij. And from this equation, we can see that the objective function now becomes decoupled, and each agent only need to solve the subproblem associated with each local data. So more specifically, in ADMM, like in each iteration, each agent will will perform these two updates: primal update and dual update. So you can see primal update is trying to update the local classifier based on the local loss function and some models from its neighbors. And after collecting, after performing the local update, and the agent will send the news model to the server, to the neighbor agents, and then each agent will perform the dual update to use the news primal model here. As I mentioned at the beginning, like the information exchange over this during this process give rise to privacy leakage, right? The question is how to make this procedure private. So we consider a differential privacy. The differential privacy provides a privacy standard for data privacy, so which guarantees that there's no much more difference between the output of algorithms over two data sets. The two data sets that differ in one data element. So mathematically, this is the definition. A randomized algorithm is called epsilon delta differentially private if for all neighboring data sets D and D prime, we have this following inequality here. And epsilon here is a privacy budget and delta is a probability of failure. So in an intuitive example, we can see like this data, and there is two data sets. Only actually this is a neighboring data set. Only the first person is different. And these two data sets input to a randomized algorithm, and we got the two output distribution, right? And the differential privacy requires that this difference between these two distributions are bounded by e to the power epsilon. Sorry. Next, I will introduce the sensitivity, which refer as a uniform stability. So defined as this equation, and which is the maximum difference between the function result with two data set D1 and D2. To achieve the epsilon delta differential property, we can use Gaussian mechanism like this one, and we add Gaussian noise to the algorithms with U is a noise, right? With variance from this equation, which is proportional to the L2 sensitivity. As we can see that the smaller sensitivity means less duration, and the smaller epsilon means better privacy, and the smaller delta means less probability of failure. So the existing work on differentially private ADMM, which mainly includes two ways. One is called the primal variable precipitation, which is at a noise primal update. And the other one is dual variable precipitation, which adds noise to the dual update. So, however, the guarantees for the differential property in this works are based on strongly functions of objective function, and also some works require a central server and to perform the model aggregation. And also, some works have significant convergence performance degradation. So our main solution is to try to add a time-varying Gaussian noise to perturb the local model in each ADM iteration. And we propose two noise variable decay schemes. And we also use the noise degree checking method to set a threshold to eliminate the two noisy primal variables from neighboring agents. And we provide the convergence analysis for generally convex objective with linear convergence rate, and provide the privacy guarantee analysis. I will introduce the technique one by one. So our idea, at the beginning, is try to add time-varying Gaussian noise to perturb the local model, right? So this is the original update, and this original update, and after we add a noise here, that means after we get the local model, and we will add a time-varying noise here to perturb the local model, and then we perform the dual update. So due to the noise injection here, so the perturbed primal variable or primal update can potentially destroy the algorithm convergence, right? So here we consider to carefully adjust the noise injection iteration to mitigate the negative effect of noise injection. So here we propose two noise decay scheme, theoretical decay and iteration decay, and this blue one and this orange one. So for example, here RP and RT here are the decay rates, and the KP for the theoretical linear decay scheme is try to decide how often to reduce the noise variance, right? Here I consider two iterations to decrease the noise variance. This is our second technique. We propose is noise degree checking. Since the result, the motivation is just like this one. So because we don't want to easily trust our neighbors, and if for example, if we have a very bad neighbor and a well-established neighbor, and they just add attribute noise to these models, and I say my neighbor is kind of outlier. So how can we remove that kind of model, right? How can we avoid this kind of bad? So basically, we provide a noise degree checking method criteria. We show in this equation, and so if it's not too noisy, we just keep using the neighbor's model, and otherwise we will not use this noise model to do the ADM updates. Then we will solve the objective function and perturb the update the model with time-varying noise decay scheme. There are two advantages of this technique. So the first thing is you can avoid Byzantine attack if some of your neighbors is compressed by Byzantine attack. You can avoid them. And another one is even your neighbor is kind of honest. Just can consider your neighbor is kind of a layer for the machine learning, you can conclude that this his contribution is not enough. So by choosing like the true noise decay scheme, theoretical linear decay scheme, and the region-based decay scheme, and we can prove that our algorithm satisfy different their different prices using the test compensation theorems. And this is a formula. This is for example here. This is a price budget related to the V is the Lifshitz constant and the eta is step size. And Vi here is the number of neighbors, and KT is the period of when doing the noise variance, and RP is the decay rate. And the next I will show the theoretical result. And this theoretical result here, we'll assume the object function is convex. And so you can see this this convex result is have 3 terms. Here, and this one. So the first term is based on is derived by the initial model parameter to the order the distance from the initial parameter to the final model, optimal model. And this term is related to the noise degree checking, this upper bound. And although these 2 terms is related to the theoretical linear the noise decay scheme which we choose. And which is things like we use specific which was a special noise decay distribution, and this term are constant. So in both schemes, like the average of function values approaches to a minimum function with converges to 1/t, and which is the same as a non-private decentralized ADML. So we conduct the simulations over adult dataset. Using adult dataset, and we consider the accuracy rate and average loss as to measure the privacy and the covariance performance. And we have some like the parameter settings to the subset to number iteration, and we consider a network generated from with cell agents. Here is the performance comparison under the simple budget among different baselines. Our algorithm is this one, is PRADMM and PRADMM here, these 2. And we can see that our algorithm under 2 decay schemes significantly outperform other algorithms and getting close to the best achievable loss, and due to the entire learning process. And this is because with carefully adjusting the purpose budget and setting a threshold to eliminate the 2 noise intermittent result, the negative effect of the noise injection can be reduced. And this is testing and training accuracy achieved by each algorithms by varying the purpose budget. Varying purpose budget increases, and we can see that our algorithms under 2 kind of noise decay scheme achieves a competitive training and testing accuracy on the wide range of values for total purpose budget. Next, I will introduce my second work focused on differentially private and communication efficient decentralized learning. So as we all know, the decentralized machine learning face 3 major challenge bottlenecks. The first one is strickling agents. Strickling agents, what these strickling agents mean? And if the commutation and speed and the commutation load of each agent may be different, which can be substantially slow down the overall system efficiency. Also, since the learning model increases, the model exchange among the agents become communication and bring a significant communication bottleneck. And the third one is the privacy concern, like the model sharing among agents introduce potential privacy leakage. So our goal is try to develop a decentralized method well they are like robust and communication efficient and privacy protection. So to deal with the straggler agents, we consider a deadline-based gradient computation. Here, this part is the fixed batch mean SGD, mean batch SGD here, and each line means different agents. And you can see the total number of running time is depends on is proportional to 1 over the minimum commutation speed. I introduce deadline time TD to let each agent can perform gradient estimation, so which can avoid waiting for the slowest agent holder for the entire network. We can also impose the context model exchange to reduce the communication overhead here into overhead. And we also consider to consider the DP mechanism to deal with the privacy challenges. We consider to add like 2 choices for adding the DP mechanism. So whether the noise should be before or after random consideration operator. So we carefully analyze both cases and give the practical guidelines for privacy and communication efficient decentralized learning. And in this work, we aim to solving this problem, which is a population risk problem, or like you can call like a stochastic learning model. And here actually is the model parameter. Theta is the data data sample drawn from an unknown distribution P. In order to instead of directly solving this problem, we consider to minimize the following yarn problem by over all the data samples D1 to DM1 here. And in collaboratively training, our goal is try to collaboratively solve this problem over n agents or n agents and connect under a communication matrix W, and the D here is the union of D1 to Dn. The D1 to Dn means the local data set. And also we assume the local the agent have a local loss function here, FRI, XDI, and overall is a local loss, local data sample. And all agents aim to collaboratively minimize the average of all local adaptive function defined as here. So with the introduction of our first algorithm, we add a Gaussian noise before the randomization. And each iteration T, each agent is given a deadline time TD to compute the gradient per sample gradient. At each end of the deadline, each agent will compute its local mean batch gradient here, and where the size of the mean batch is not deterministic but a random variable. So we denote the processing of each machine learning the computer speed as a VIT, and withdrawn from a distribution FVV, and so we can get the size of mean batch is defined VIT times TD. And in order to enforce differential privacy, each agent will add a noise theta IT drawing from this from a distribution, Gaussian distribution, to perturb this term local gradient. After that, each agent will using the previous local model and the context model from neighbors, and also the perturb the gradient to update is a new local model XIT plus 1. And WIG here is the weight of communication. If agent I and G are not neighbor, WIG equals 0. And alpha, epsilon, and alpha here are positive constant, or like you can treat it as subset. And here is a privacy analysis. We can see like this parameters. We can see like our algorithm satisfy epsilon the different privacy with a specific budget here. And due to the deadline-based gradient, we introduced deadline-based gradient computation. Right, the price budget is related to the size of XIT, and so it can provide a good way to describe the privacy loss accumulation of decentralized learning under a regular delay problem. And when you know, like for example, here is the original local model training, like it's include like the perturb the local model, previous perturb the this is a low gradient, the local model, and the noise from the context local model from its neighbors. And if there's no, we consider the case if there are no gradient commutation. So that means like the empty of mini batch is the size of mini batch is 0. So the each agent I will update only the first part. So and sending the context model to the neighbors without spending any perspective while preventing the stragglers holding up the entire network. So in the first algorithm, the DP noise is applied before the random quantization. So the privacy guarantees of quantization operator roots from the post-processing of different privacy. So the question here is how about we add noise after random quantization? So the challenges is that like if we directly add Gaussian noise after the quantization, the transmit value now become real numbers, and the benefit of the model quantization are lost, right? So our solution is try to sample noise from a discretization of the Gaussian distribution and a discrete Gaussian noise to the context value without sacrificing the communication efficiency. And the eta here is the scale factor, and z is the integer. So the question is, however, like the question is become whether this discrete Gaussian distribution still guarantees the different price or not. We can define like a discrete. We have shown that like we have proved that even we add noise from the discrete Gaussian distribution, and we can still satisfy the epsilon delta differential pricing. This figure means here. This means like here the sample value are from integer. Here we add this kind of noise to the model pair to the context value. In particular, at each iteration t, each agent will perform the database gradient computation and then update the local model by using the shared differentially private context model from neighbors. Here, the discrete noise, right, drawn from discrete noise distribution and product the context model will plus the discrete noise to its neighbors. And some differential privacy is achieved by perturb here, right? And this theorem shows like the privacy guarantee result, and we can see that like this is some more spectral value here. We can see that the perspective is related to the step size epsilon and the scale factor eta and the model direction p. And reducing the step size alpha and eta not only help balance the randomness introduced by exchanging the context model and private local models, but also improve the privacy guarantee. So here we show the convergence analysis of our algorithm. We first give like 4 assumptions. The first one is the weight matrix, the communication matrix is symmetric and doubly stochastic, and also the random quantization Q is unbiased and variance bounded, and the loss function is k-Lipschitz continuous, and the stochastic gradients are unbiased and variance bounded. And we show that both of algorithms satisfy for non-convex loss is satisfied have the same convergence rate and consensus rate here. And the convergence rate like means that like the iterate generated by the algorithms can find a stationary point, and the consensus rate means like the local model will close to each other. Under like the strongly convex loss function and the previous 4 assumptions, and we focus on the population risk analysis. And the population risk defined like Fn minus F star here. The Fn here, this part is the empirical risk, and F star is a population risk. This is to the result of these two algorithms, we can see that our risk of the second one is this one, and which is higher than that of the first algorithms. This is our experiment setting. We conduct simulations over MNIST and CFR10, and the baselines include decentralized SGD with a fixed batch size and no quantization. And we also consider a baseline sparse differential Gaussian mask the stochastic gradients, which consider a fixed batch size. And they try to share the compress the differentials to the neighbors. And the S here is a sparsification operator, and the data here is a Gaussian Gaussian noise to inform differential quantity. And we set the commutation speed from uniform distribution, and deadline time TD. And here the TC means the communication time of a p-dimensional vector without transition. And we consider a network with generated from a general of 10 agents. And here is the experiment result on MNIST and CFR10. And we can see that our proposed algorithm, like this one and this one, is can outperform the baseline algorithms in terms of total runtime, and this loss is runtime. And the utilization of quantization and deadline-based scheme can reduce the communication cost while mitigate the strict delay problem. And the second algorithm have lower performance compared to the first one, which is consistent with our theoretical analysis. And here is the experiment result on the model performance of different number of agents and with large batch size. And on this part, we can see that compared to other methods, our approaches continue to have better performance for large network. And on this part, we can see that the large batch size can further reduce the loss while consuming more training time. Next, I'll introduce my third work, really differentially private and fair machine learning. So this is an overview of the procedure of training machine model. We have a lot of users contribute a lot of data, and the data and we train a machine model or this data, and we use this machine model to do the machine learning decision. However, there are growing concerns about the potential unfairness issues and price leakage during this training and deploying procedure. So since the adversary may perform the various attacks to these models together with some background knowledge to infer sensitive information in the training data set. For unfairness issues, a classification model of a job hiring system is more likely to hire candidates from a certain racial or gender groups. So, but why machine learning machine model are biased? Generally speaking, the bias can be introduced through the training data and machine learning algorithms. The training data is collected by humans, right? Humans are often biased. So human bias is propagated to data set, and then to predict to the prediction of the model. And the learning algorithms itself may also introduce bias. That's because the model tends to fit the majority group better. Yeah, because the machine algorithm is to minimize the average loss. So the goal here is to try to design machine learning model will achieving fairness and privacy protection. So in this work, we aim to solve this problem, an integer risk problem. And here the D is a local data, W is a model. And the D include the N data samples DI, and the DI actually is a tuple. And the DI includes three terms, XI, ZI, and YI. XI means the unprotected attribute, and the ZI means the protected attribute. And the label YI is YI is a label. And what the protected attribute means? The protected attributes means that the attributes can be used to identify a group of people, like a gender, like gender, race, or age, something. And when the protected features are not used well properly, it may introduce the machine learning discrimination. For example, introduced at the beginning, the job hiring system, facial detection applications here. So to quantify the discrimination, we consider the most widely used fairness definition called demographic parity. The demographic parity is applied to a group of samples. So it requires that for any predictor one height, the probability of positive prediction are the same regardless of the group is productive or not. Consider this table, and a data set used to predict whether a person should be here or not. This is a prediction, and each data have 3 features: race, skills, and years of experience. And it consider and you see the protected attribute in this table is race. Yeah, and so we consider this group the Hispanic group. We can see that for Hispanic group, each person have a 50% positive rate to be predicted as a hair, right? And for the white group, it only has 100% to predict as a hair. So that's what that means. That means like the predictor does not satisfy the demographic parity, since like the prediction for yes is not regardless of the Hispanic group and the white group is not equal. So how to enforce the fairness to achieve this probability equal? So the main solution we consider here is called decision boundary fairness. So the key idea of this method is try to limit the cross covariance between the protected feature value and distance from the decision boundary. And as this problem show, to introduce the to ensure the fairness fair classification, we need to find a model parameter W that minimize the loss function under a fairness constraint. JDW here is a fairness constraint. The JDW is related to this one. You can see Zi is the protected feature, and height Z is the average of protected attribute, and DXIW is the decision boundary. So for logistic regression, the decision boundary is defined as SIT times W, and the fairness constraint for logistic regression is like this one. So here we show the effects of enforce that kind of constraint. So consider classification task. The red line here is a decision boundary. So actually, it's obviously a perfect classifier because like 2 sets of data samples, square and circle, are well classified, right? But it shows pairs with respect to the color. Suppose the color means like different groups. Well, for example, the blue means male, the green means female. Among the blue samples, we can see that we have 58% of positive rate. That means 7/12. But for green samples, we only have 25% positive rate because like 1/4. So by moving around the decision boundary in this position, this can be achieved by enforce this fairness constraint. And now the classifier is not perfect because 2 examples are misclassified. But now this classifier is become fair because like the green are 2 positive, 2 negative, and the blues are 6 positive and 6 negative. And so now is achieve the demographic parity. So to deal with the privacy concern, we consider a functional mechanism, which is injected the random noise to the objective function, the polynomial coefficients of the objective function, and then publish the noisy model parameters by minimizing the perturb objective function. So for example, if we consider a logistic regression model, like this one, and which is not a polynomial, in order to use the functional mechanism, we need to first write the polynomial of the objective function. We expand at this point, we can get the Taylor expansion and with this coefficients. Since this equation involves in infinite summation, so the term of fk0 here involves in the equation that not have closed form solution. So the functional mechanism is to do a truncation first, and then we get like the truncation, the polynomial loss, and this is the parameter first, and then the functional mechanism will add the noise to the perturb the coefficients here, and then solve the perturb objective function. We can get a differential parameter model. So in our case, like we propose a calibrated function mechanism. So since like our two requests, one is to try to achieve fairness and different parts, right? So consider to enforce the fairness, we consider the determinate boundary fairness to enforce the fairness constraint to the loss function. And we first to transform it into an unconstrained problem by treating the fairness constraint as a penalty. And to enforce the differential property, we write the polynomial approximate objective function, and here is the coefficients, and we then will introduce then a noise to perturb these coefficients, and to enforce differential property. The case is since like for example, since this data set, for example, since the attribute involved in the data set may be not independent from each other, which means some unprotected attributes are correlated with the protected attribute. For example, here in this case, the protected attribute is a race, and there is unprotected attribute is often goes to Mexican markets, right? And it's you are quite correlated to the race. So so we consider to add more noise to the coefficients contained to contain particular attribute, unprotected attribute, and less noise for others. So by doing this, the connection between the unprotected and protected attributes are weakened, and also reduce the model discrimination. And also like since we add more noise to some like specific attribute, and it can further prevent the model inversion attack on this attribute. Next, this is the experimental setting. We conduct simulations over adult data set, and it includes 13 different features. For example, work class, education, race, age, gender, and so on. And the baselines are logistic regression and a PFLR star, and enhance the differential property in a fair logistic regression method. This method is injecting noise with shift mean to the objective function of the logistic regression and with fairness constraint. And we consider two metrics for the performance. One is accuracy, the other one is the risk difference. The risk difference is defined, you can see only the positive rate over two groups, z equals to 1 and z equals to 0. And we consider the parameter setting is like this one. We consider binary protected attribute is gender. Here we study the accuracy comparison among the baselines, and here our two algorithms is this blue one PDFC and ADFC. PDFC is try to add a Laplace noise and the ADFC is the Gaussian noise. And in this figure, and we consider like the particular unprotected attribute is marital status. And this L-less regression, this is baseline PL4 star. This is our two algorithms, and we can see that our ADFC is achieve much better accuracy than the baselines over in all PROX region. But like the PDFC outperforms the baselines when usually small. And we also evaluate the effect of choosing different particular unprotected attribute, and by for example marital, age, or something. And we can see that like choosing different attribute has different effect on the accuracy. And the next I will show the risk difference comparison. The risk difference, smaller value is better. And here, like these two are baseline, and these for our algorithms. We consider like the unprotected, particular unprotected attribute as race and marital status. And we can see like in this way, like too small press budget here, and leads to low quality model since too noisy added to the coefficients, and it introduces a lot of variance also. And when the privacy budgets are large and the negative of noise injection is reduced, so the fairness constraint can be fully enforced. So when comparing the result over the race and marital status, we can see that we can see that there are more correlation between the marital status than the race. And more correlation than like the marital status with the gender and the race and gender. And overall, our approach is perform better than the best baselines. In my future work, I will continue my investigation on privacy, efficiency, and the fairness of machine learning. So for studies of the private collaborative learning, we have proposed several differentially private ADM based to balance the algorithms to balance the trade-off. However, the privacy analysis and the convergence rate of our current approach is still rely on the convexity and the smoothness of the objective function. So we try to consider like how to relax the strict assumption, and we also try to consider some like several adaptive privacy allocation schemes to balance the privacy and utility trade-off, and also plan to integrate the proposed algorithm into real-world systems. And my current work on robust and efficient collaborative learning, we need to assume that each agent has access to data generated ID. However, in practice, in practice, we need to design the robust and efficient collaborative learning algorithm, right, which can tolerate the limited availability of the clients and limit the reliability of network and the heterogeneous of data distribution. So to address the issues of privacy and fairness and discrimination in machine learning, we have designed several algorithms by jointly combining the functional mechanism and decision boundary fairness. One popular approach in machine learning is use like a SGD, stochastic gradient descent. So I will just consider how to mitigate these parity effects of different privacy in learning SGD framework. And also, we will try other fairness criteria, for example, equality and prediction and parity. This is my publication. And finally, I will give a conclusion. So in my presentation, we first propose a robust and differentially private ADM algorithm by introducing several techniques to break limitations of existing works, and like several noise variance decay schemes. And we also propose two GPT SGD algorithms, which can achieve robust communication efficient and privacy protection for decentralized machine learning. And we consider like a deadline-based gradient computation, random quantization technique, and alternative design of deep knowledge injection. And we also propose like several algorithms to learn machine learning model with differential privacy and fairness constraint by applying the functional mechanism and decision boundary fairness. Thank you. That's all.